All right, here it is. So we talked about limits already, and now we're going to talk about them a little bit more for 3.1 especially. And we're going to define the derivative in terms of a limit. First, let us talk about what it is in terms of a graph. So this is the picture you want to remember for the rest of the class. There's some function doing its little thing in the plane there. And what I would like to do is I'd like to find the slope of said function at A. Find the slope of the curve at a particular point. In our example, that point is A comma f of A, right? That point is going to be right here. I want to find the slope of the curve at that point. Okay? All right, so the slope of the curve we're going to define. Definition, slope of a curve at a point is the slope of the tangent line at that point. That's a definition. Not that we got nothing. So what we would like to say then is, if I were to draw a line which is tangent to the curve at this point, I will make it purple. Hopefully it'll be somewhat tangent looking. Is that believably tangent? No. Is it believable? No?
No.
What? Why not? Come on, practically. Perfectly almost. Right? This line just grazes the curve at A comma f of A. That's all it does. Just grazes it. Okay? So if that's the case, then the slope, I'm just erasing it with the thing. I'm supposed to be writing it, not erasing it. So then slope of purple line is slope of curve at A f of A. Okay? Slope of the curve is the slope of the tangent line. So what we really need to get a handle on is the slope of the tangent line. Try to make the idea of slope of a curve more concrete. So it's the slope of the tangent. Okay, I know all about lines. What we're going to do is this. I wish I had more colors, but whatever. All right. So, hold on 1 second. Just 1 second. Come on, lucky nerve. Okay, never mind. What we're going to do instead of finding the slope of the tangent line at first, we're going to find the average slope of the curve. So I'm going to pick a point which is further out from A. We'll say right about here. Okay? And we're going to draw a line, a segment at least, between them. This is called a secant line. Secant line. What is the slope of the secant line? Slope of secant line is the average rate of change, right, of the curve. There's some point there, x comma f of x. X is some value away from A. Slope of secant line is the average rate of change. Average rate of change of f of x from A to x, whatever you want to call it. Maybe I'll call it b. I don't know, whatever b. Just pick some value here. Okay. This is the very first question they had you answer, I think, in section 1.1 in the online homework or something. It's about average rate of change, right? You correct? Okay. And they gave you maybe pictures like this, I'm not sure. Okay? So this is a secant line, and the slope of the secant line is an average rate of change, right? From here to here, how did this curve get from here to here? Well, Well, approximately the rate of change, which would be this slope, right? It's true. It's not really that rate of change, right? It changes very subtly all the time, right? Here's one place where it'll be exactly that. So, how would you write the slope of that secant line? In the notation that I've given on the board, f of x, and a's and b's and whatnot, how would you write the slope of that secant line? Slope of secant line. How would it be written? Right. F of b minus f of a over b minus a, right? Which is the same as saying y2 minus y1 over x2 minus x1 equals slope of secant line. Correct? That's the slope. Delta y over delta x. Okay. Since this is a line, unlike the curve, this line has a constant slope, which we can describe as just these 2 points, right? But that slope does not describe this tangent line down here, right? And that's what we really want to get to. Say again? I will not make a triangle. Although I do like making triangles, and I'm tempted because you said that, I'm not going to make a triangle though. What I'm going to do instead is I'm going to call this, instead of b, I'm going to write it back as a, because it's any distance away, really. This is really any secant line, okay? So this would be a particular value of b. As you all know, a, b's, and c's are used for constants. So I'm going to use x again, just for a brief moment. I just want to recognize it as the slope of the secant. So this would be what? F of x minus f of a over x minus a. Okay, that'd be a slope over a secant for any secant. Now, what I want to do is I want to push this dot here. I want to push it further down the curve. If I push it further down the curve, let's say to, I don't know, halfway between, put it there. Then the new secant line has a slope which is closer in value to the slope of the tangent line, which I want to get to. Agreed? I understand that the line's getting kind of tiny, but it still has a constant slope. And its value, you would agree, is certainly closer to the slope of the tangent line than this one was previously. We could do that indefinitely. Let's just keep pushing this dot closer and closer, a little bit closer here, and the picture's getting a little messy. But then it'd be, even more closely approximating the purple line slope. Agreed? And we could just keep pushing and pushing what? What am I pushing? I'm really pushing, as I push this dot down this curve, what I'm really doing is I'm pushing x closer to a. Right. So what I want to do is I want to take the limit as x approaches a. So that is called a derivative. Derivative. That is slope of tangent line to the curve. At x equals a. I want the slope of the tangent line of the curve at x equals a, which means the slope of the curve at x equals a, because they're the same thing. Slope of the tangent line, slope of the curve is the same. So I'll do what you just said. I will simply take the limit as x approaches a of this